What if you could hold the weight of all of humanity in the palm of your hand, not the metaphorical weight of our history, our hopes, or our dreams, but the literal physical mass of every single person on Earth? A staggering 500 million tons of matter compressed beyond all recognition into a sphere no larger than a child's toy marble. It is a concept so alien, so fundamentally at odds with our lived experience that our minds instinctively recoil. The laws of nature as we know them scream that this is impossible. The atoms that form our bodies, our world, the very air we breathe are defined by space, the vast empty gulf between a nucleus and its orbiting electrons. To create such an object would require a force so titanic, so overwhelmingly violent, that it could shatter that fundamental atomic structure, crushing the very identity of matter, and forging something new, something terrifying from the ruins. And yet the universe not only performs this impossible feat, it does so with a terrifying regularity. Out in the cosmic dark, in the graveyards of colossal suns, lie the shattered remnants of stars that have done exactly this. They are the universe's most extreme creations, the densest objects we have ever discovered, second only to the unknowable singularity of a black hole. They are the cinders of stellar giants, the ghosts of cosmic royalty condensed into a form that defies our earthly intuition. These are neutron stars, and they are not just monuments to unimaginable pressure. They are the source of a profound and unsettling mystery, a paradox that pushes our understanding of physics to the absolute breaking point and perhaps beyond it. They are engines of creation and destruction, wrapped in a riddle that we're only now beginning to unravel, a riddle that whispers of new laws of nature, of forces we have yet to name. To understand these cosmic enigmas, you must first witness their birth. It is a story that does not begin with a gentle glimmer, but with the most spectacular death in the known universe, a supernova. Picture a star not like our own sun, but a true leviathan of the cosmos, a blue supergiant hundreds of times more massive, burning with a ferocity that makes our star look like a flickering candle. For millions of years, this celestial titan lives in a state of exquisite balance, a constant war waged within its core. In one corner, the relentless inward crush of its own immense gravity, a force trying to squeeze the entire star into a single point. In the other, the explosive outward push of nuclear fusion, the same process that powers our sun but magnified to an unimaginable scale. Deep within its heart, this stellar furnace forges hydrogen into helium, then helium into carbon, and continues up the periodic table, creating oxygen, neon silicon, each stage of burning, growing hotter, faster, more desperate. It is a magnificent act of cosmic alchemy, the birthplace of the very elements that make up planets and life and you. But this process cannot last forever. The star is living on borrowed time, its fuel dwindling with every furious pulse of energy. The end comes when the core, having exhausted all lighter fuels, finally creates iron, and with iron the fire goes out. Iron is the universe's dead end for fusion. Fusing iron atoms doesn't release energy, it consumes it. The delicate balance that defined the star's entire life is shattered in an instant. The outward radiation pressure from the core vanishes, and gravity, the patient ever-present victor, finally claims its prize. The consequences are immediate and catastrophic. The star's iron core itself, more massive than our entire sun, begins to collapse under its own weight. In less than a second, a celestial object that was thousands of miles across implodes, crushed down to a sphere barely the size of a modern city. The speed of this collapse is breathtaking, reaching over 70,000 kilometers per second, a quarter of the speed of light. The outer layers of the star, now left with nothing to support them, begin a terrifying freefall, plummeting inwards towards the impossibly dense, newly formed core. The temperature and pressure skyrocket to levels that are difficult to even comprehend, hundreds of billions of degrees, densities trillions of times greater than water. It is in this crucible of cosmic violence that the fundamental laws of matter are rewritten. The crushing force is so immense that it overcomes the powerful repulsion that keeps atomic nuclei apart. Electrons which once orbited their atomic homes in peaceful solitude are violently slammed into their protons. A positive charge and a negative charge are forced together, cancelling each other out, and creating a new particle, a neutron. This process, called electron capture, sweeps through the collapsing core like a wildfire. What was once a mixture of elements, a rich stellar soup, is transformed into a single pure substance, a sphere composed almost entirely of neutrons packed together as tightly as the laws of physics will allow. A sea of neutrons, a single gigantic atomic nucleus the size of Manhattan. This, the brand new neutron star, has been born. But the cataclysm is far from over. As the outer layers of the star continue their inward plunge, they slam into the surface of this new, unyieldingly hard neutron core. The impact is apocalyptic. The material doesn't just hit the core, it rebounds. It creates a shockwave of unimaginable power, a supersonic tsunami of energy and matter that tears back outwards through the falling stellar layers. This shockwave, supercharged by a torrent of ghostly particles called neutrinos pouring from the newly formed neutron star, is the supernova explosion we see across the universe. It is an eruption of light so brilliant it can outshine its entire home galaxy, a blast that seeds the cosmos with the heavy elements forged in the star's life and death. For a few brief, glorious weeks, it is the brightest thing for billions of light years in any direction. And when the light finally fades, when the cosmic dust settles, what remains is an expanding, shimmering cloud of gas, a nebula, the beautiful tombstone of a dead giant. But at its heart, silent and unseen, sits the newborn corpse, the cosmic cinder, the ghost in the machine. A city-sized sphere containing the mass of 1.5 suns, a gravitational monster so powerful that a single teaspoon of its substance would weigh more than all the mountains on Earth combined. To visit one of these objects would be to enter a realm of physics torn from a fever dream. Spacetime itself bends and warps in its presence, a deep gravitational well that distorts the path of light from distant stars. Its surface gravity is 200 billion times stronger than Earth's. If you could somehow stand upon it, you would be instantly flattened into a microscopic smear of atoms, your body's mass converted into a blinding flash of energy. This is not a world of mountains and valleys, but a landscape of utter perfection. The immense gravity smooths its surface to a mirror finish, with any irregularities unlikely to be more than a few millimeters high. And yet this seemingly simple object harbours a bizarre and complex interior, a place where matter behaves in ways we are still struggling to model. Just beneath its crystalline iron crust, physicists believe the immense pressures squeeze neutrons into strange exotic shapes. They form long, spaghetti-like strands and wide, lasagna-like sheets, a state of matter whimsically named nuclear pasta. Deeper still, at the very core, the pressure may be so great that the neutrons themselves break down their constituent quarks, dissolving into a frictionless superconducting soup, a state of matter not seen anywhere else in the universe. But it is not just the density that makes a neutron star so alien. As the original star collapsed, it conserved its angular momentum, much like an ice skater pulling in their arms to spin faster. But this is a spin-up on a cosmic scale. The parent star, which may have taken weeks to rotate once, has now shrunk its radius 1,000,000-fold. The result is a rotational speed that is almost beyond belief. Many neutron stars spin hundreds of times every single second, their equator moving at a significant fraction of the speed of light. They are the most perfect gyroscopes in the cosmos, their spins so stable that their clocks are more accurate than any we have built on Earth. This rapid spin, combined with the star's original magnetic field, compressed into a much smaller volume, generates the most powerful magnetic fields known to exist. These fields are quadrillions of times stronger than Earth's, a force so potent it could warp atoms into thin needles and erase the data from every credit card on our planet from halfway to the moon. This combination of rapid rotation and intense magnetism turns some neutron stars into what we call pulsars. They act like cosmic lighthouses. As the star spins, beams of intense radiation generated by particles accelerating in its magnetosphere sweep through space. If one of these beams happens to intersect with Earth, our radio telescopes detect a precise rhythmic pulse, a steady cosmic heartbeat ticking away across the interstellar void. For decades, we saw these objects as magnificent but predictable cosmic clocks. They were the orderly, well-behaved remnants of a chaotic past. We believed their defining characteristic was their immense gravity, their ability to hold on to matter with an unbreakable grip. We thought we understood their story, a violent birth followed by a long, quiet existence, as a spinning, cooling cinder slowly fading into the darkness. We were wrong, because something utterly paradoxical is happening around these stellar corpses, something that defies the very nature we assign to them. From the poles of these gravitational anchors, these ultimate prisons of matter, something is escaping. And it is escaping with a ferocity that makes every other stellar wind in the cosmos seem like a gentle whisper. Our own Sun, a dynamic and powerful star, constantly breathes out a stream of charged particles known as the solar wind. This wind travels at an impressive clip, typically around 400 kilometers per second, or about 1,000,000 miles per hour. It fills our solar system, buffets planetary magnetic fields, and paints the polar skies with the shimmering light of the aurora. It is a powerful force of nature by any human standard. But what we are now detecting from neutron stars is in a completely different category of existence. From the hearts of nebulae powered by their central pulsar, astronomers have found evidence of particle winds that beg a belief. These are not gentle breezes. They are relativistic jets, fire hoses of matter and antimatter electrons and their antimatter counterparts, positrons blasting away from the neutron star's magnetic poles. And their speed is astonishing. They have been clocked at over 100,000 kilometers per second. In some cases, they are accelerated to more than a third of the speed of light. This is not just a little faster than our solar wind. It is up to 1,000 times faster. It is a torrent of particles so energetic that when they slam into the surrounding interstellar gas, they create vast glowing shockwaves, pulsar wind, nebula, celestial masterpieces painted by an unseen, impossibly powerful celestial blowtorch. And here lies the profound, unnerving mystery. How can an object defined by its almost inescapable gravity, an object with a gravitational pull so strong it can bend light itself, be the source of the fastest and most violent particle winds in the universe? It is a contradiction that strikes at the heart of our understanding. Common sense dictates that the star's gravity should capture any particles nearby, pulling them back down to its surface. Generating an outflow is hard enough. Generating one that moves at a significant fraction of light speed from such a deep gravitational well should be impossible. It's like discovering that the floor of the deepest ocean trench is somehow the source of a geyser that shoots water into outer space. The energy requirements are staggering, far beyond what simple thermal processes could explain. Something else is happening here, some exotic mechanism born from the nexus of extreme gravity, insane rotational speeds and godlike magnetic fields is acting as a colossal cosmic accelerator. It is a process so efficient, so powerful, that it tears matter and antimatter from the vacuum of space itself and flings it across the galaxy with almost perfect efficiency. This phenomenon is not just a curiosity, it is a direct challenge to our established theories. The models we use to describe the behavior of plasma and magnetic fields, models that work beautifully for our Sun and other stars, simply break down when confronted with the extremes of a neutron star. They cannot account for the sheer velocity and power of these winds. The physics we know appears to be broken, or more likely it is simply incomplete. These stellar ghosts are trying to tell us something. They are hinting that in these extraordinary cosmic laboratories, where matter is pushed to its absolute limits, new physical principles come into play. They are forcing us to confront the possibility that our neat and tidy laws of nature are but a local approximation, and that the true, universal laws are far stranger, more powerful and more mysterious than we ever dared to imagine. Unlocking the secret of these winds is more than just solving a fascinating astrophysical puzzle. It is about finding the missing pieces of our cosmic rulebook pieces that can only be found here in the heart of a dead star's impossible storm. It began not with a bang, but with a flicker, a strange, impossibly regular pulse etched onto miles of chart paper in the quiet English countryside of 1967. To the young radio astronomer Jocelyn Bell Burnell, it was an anomaly, a faint bit of scruff that appeared with such clockwork precision it defied any natural explanation she knew. It was so alien, so seemingly artificial, that for a few tantalizing weeks she and her supervisor half-jokingly labelled the signal LGM-1 Little Green Men. It was a profound, thrilling and slightly terrifying possibility. Were we finally hearing a deliberate message from across the gulf of space, a cosmic lighthouse perhaps, or the heartbeat of an extraterrestrial machine? The truth, when it was finally pieced together, turned out to be far stranger, and in many ways far more violent and consequential than any alien intelligence. The signal was not a product of biology, but of physics pushed to its absolute breaking point. It was the cry of a celestial ghost, the remnant of a star that had died in a titanic explosion, leaving behind an object so dense, so bizarre it barely seemed possible. What Bell Burnell had discovered was a pulsar, and the pulsar was our first glimpse of the universe's most extreme creation, the neutron star. To understand this object is to abandon everything your intuition tells you about the world. You have to unlearn the familiar concepts of matter space and gravity. Imagine a star far more massive than our own sun, reaching the end of its magnificent life. It has spent billions of years fusing elements in its core, a celestial furnace, holding back the relentless crush of its own gravity. But now, the fuel is gone. The delicate balance is broken, and in an instant, gravity wins a catastrophic victory. The star's colossal outer layers are blasted away in a supernova, an explosion so bright it can outshine its entire galaxy for weeks. It's one of the most energetic events in the cosmos, a final glorious death rattle. But our story isn't about the explosion. It's about what remains in the heart of that celestial firestorm. The core of the star, a mass perhaps 1.5 times that of our sun, collapses inward under a gravitational force that is simply beyond comprehension. It doesn't stop collapsing at the stage of a white dwarf where the pressure of electrons prevents further collapse. Here, the gravitational onslaught is so overwhelming that it shatters the very structure of the atoms themselves. Think about the atoms that make you, me, and everything on Earth. They're almost entirely empty space. An electron orbits a tiny nucleus at a vast relative distance. If a nucleus were the size of a marble in the centre of a football stadium, the electrons would be like motes of dust out in the bleachers. Gravity in the core of a dying star erases that stadium. It crushes all that emptiness out of existence. The immense pressure physically forces the negatively charged electrons into the positively charged protons within the atomic nuclei. They merge their charges, cancelling out, and in a process governed by the weak nuclear force, they become something new: neutrons. An entire star's worth of matter compressed into a sphere of pure neutrons packed together as tightly as the laws of quantum mechanics will allow. The result is a neutron star. A star with 1.5 times the mass of our sun, an object over 1 million kilometres wide, crushed into a ball no larger than a single city, perhaps just 20 kilometres across. The density is a concept our minds are simply not built to grasp. A single teaspoon of neutron star material would have a mass of over 1 billion tons. It would weigh more than all of humanity combined. A sugar cube of this substance would exert the same gravitational pull as the entire Himalayan mountain range. This isn't just dense, it is the end of density. It is matter so compacted that its internal pressure, the nuclear force that stops protons and neutrons from occupying the same space, is the only thing preventing it from collapsing further into the ultimate unknown, a black hole. It lives its life perpetually on the edge of that abyss. This substance, which physicists call neutronium, is a soup of subatomic particles, behaving in ways we can only model with our most advanced theories. It is likely a superfluid state of matter with zero viscosity, meaning it flows without any friction at all. It is also a superconductor conducting electricity with perfect zero resistance efficiency. It is an object of superlatives, a testament to the universe's capacity for the extreme. And from this impossible density, a second, even more dominant force emerges: gravity. According to Einstein's general relativity, gravity is not a force in the classical sense, but a curvature in the fabric of spacetime itself caused by mass. A planet like Earth creates a gentle dimple. A star like our sun creates a deeper well. A neutron star, however, doesn't just create a well, it creates a vortex. It warps the space-time around it so severely that it behaves like a cosmic plug hole. The escape velocity from its surface is staggering more than half the speed of light. If you could stand on its surface a crust of crystalline iron beneath your feet and throw a ball upwards as hard as you could, it wouldn't just fall back down. It would strike the ground again with the force of a nuclear bomb. Light itself, the fastest thing in the universe, struggles to climb out of this gravitational pit. Photons leaving the surface lose so much energy in the fight against gravity that their wavelengths are stretched, their colour shifted towards the red end of the spectrum. This is gravitational redshift, a direct visible consequence of Einstein's theory in action. This gravity is an almost perfect prison. It is a fundamental property of the neutron star, a defining characteristic that says nothing leaves. But the violence of its birth gives it two other extraordinary properties. As the original star's vast core collapsed, it obeyed one of the most fundamental laws of physics, the conservation of angular momentum. It is the same principle you see when an ice skater pulls in her arms to spin faster. The star's core, once rotating perhaps once a month, shrinks by a factor of hundreds of thousands. Its rotational speed increases by a similar mind-boggling factor. The resulting neutron star is a spinning top of cosmic proportions, whipping around on its axis not once a day or once a second, but hundreds of times a second. It becomes a gravitational gyroscope so stable in its rotation that its pulse, the beam of radiation sweeping past our line of sight, makes for one of the most accurate clocks in the entire universe. This dizzying spin, combined with the superconducting interior, forges the neutron star's final weapon, its magnetic field. Just as the spin was amplified, the original star's magnetic field is also dragged inward and concentrated into an unimaginably small volume. The result is a magnetic field 100 trillion times stronger than Earth's. This is not just powerful, it is a force that reshapes reality around it. It is so intense that it would distort the electron clouds of any atom that came near it, rendering chemistry as we know it impossible. It is a celestial dynamo, a spinning super-dense magnet creating a vast and complex magnetosphere that crackles with energy and unleashes torrents of high-energy particles. It is this magnetic field coupled with the ferocious spin that generates the beams of radio waves that Jocelyn Bell Burnell first detected. The pulsar's lighthouse beam is a product of this electromagnetic engine, a scream of radiation powered by the star's slowing rotation, flung out into the cosmos for eons. So here we have our portrait painted with the known laws of the universe. We have a foundation built on three pillars of modern physics. First, Einstein's general relativity, which describes the overwhelming gravity, the warped space-time that defines the star as a cosmic prison. Second, the laws of electromagnetism, which explain the colossal magnetic field, the dynamo that powers the pulsar's lighthouse beam. And third, the nuclear and quantum forces which dictate the very existence of neutronium, the strange state of matter that stops the star from becoming a black hole. These are our rulebooks. They are the tools we have used for a century to decode the cosmos, and in almost every instance they have proven triumphant. They describe the object with breathtaking accuracy. They predict its behaviour, its stability, its emissions. They tell us what a neutron star is. And they all point to the same inescapable conclusion: a neutron star is an anchor. It is a place where matter goes to die, a gravitational fortress defined by its power to pull things in and never let them go. To truly appreciate the paradox we're about to confront, we must first look homeward to our own star, the Sun. The Sun is not a quiescent ball of light. It is an active breathing star, and it constantly exhales a stream of particles into space. We call it the solar wind. This isn't a wind in any terrestrial sense. It is a tenuous supersonic outflow of protons and electrons boiled off the Sun's seething outer atmosphere, the corona, which is paradoxically hotter than its surface. This wind is driven by immense thermal pressure, a heat so intense that gravity can no longer hold on to these energetic particles. They are flung outwards, travelling at a brisk but on a cosmic scale relatively gentle 400 kilometers per second. This wind flows past Earth, shaping our own magnetic field, giving rise to the aurora. It journeys to the edge of our solar system, carving out a protective bubble called the heliosphere, which shields us from the harsh radiation of deep space. The Sun's wind is a life-giving force, a constant sigh that defines our cosmic neighbourhood. But even this requires a monumental effort. The Sun is in a perpetual battle with itself, its immense gravity trying to pull every particle back, while its thermonuclear furnace provides just enough outward pressure for a tiny fraction of its mass to escape. It is a balanced, well-understood process. Gravity pulls, pressure pushes. Now return with us to the neutron star, an object with a gravitational pull 200 billion times stronger than Earth's, trillions of times stronger than the surface gravity of the Sun, a place where the escape velocity is half the speed of light. The rulebook is clear. General relativity is unambiguous. Nothing should be able to escape this prison, let alone ride a gentle wind away. The sheer force required to lift a single particle from its surface is astronomical. Any notion of a stellar wind, a gentle outflow like our Sun's, should be utterly laughable. It would be like a whisper trying to escape the epicenter of a nuclear detonation. The physics that so perfectly describes the star itself seems to erect an impenetrable wall forbidding any significant mass from ever leaving its grasp. And yet, it happens. We have observed neutron stars that are not just anchors, but engines. They are not just prisons, but cannons. They are unleashing something that dwarfs the solar wind into utter insignificance. We have seen particles accelerated away from these spinning embers, forming vast, shimmering nebulae that glow with power. These are not gentle breezes. They are hurricanes of matter and antimatter blasting outwards at speeds that are not just fast, but fundamentally shocking. We see winds moving at over 1/3 the speed of light. That's 100,000 kilometers per second, 1,000 times faster than the solar wind. This is the fundamental contradiction, the ghost in the machine of our cosmic understanding. How does this object, the universe's ultimate prison, generate the most ferocious winds known to science? What mechanism, what unknown force, what new physics could possibly overcome that godlike gravity and accelerate particles to such insane velocities? The very pillars of our knowledge, relativity, electromagnetism, nuclear forces which so beautifully construct the neutron star, fail to explain its most violent outburst. The model is broken. The rulebook is missing a chapter. The scream we hear from these objects is not just a beam of radio waves. It's the sound of our physics being torn apart, forcing us to confront a mystery that lies in the turbulent high-energy frontier between the known and the truly impossible. So we had to build new eyes, not of glass and mirrors alone, but of crystal and silicon, designed to perceive a universe that shines in energies far beyond our vision. We turned our gaze upwards, armed with instruments of almost unimaginable power, focusing them on the pinprick locations of these cosmic phantoms. At the vanguard of this new assault on the unknown stood the Chandra X-ray Observatory, a celestial predator hunting for the most violent phenomena in the cosmos. Floating in the cold vacuum far above the blurring veil of Earth's atmosphere, Chandra's exquisitely polished mirrors could resolve the faint energetic whispers of matter heated to millions of degrees. It was designed to see the fury. Alongside it, the venerable Hubble Space Telescope, our steadfast eye in the visible and ultraviolet, provided the crucial context mapping the aftermath of these stellar tempests, tracing their ghostly impact on the surrounding interstellar medium. Together they formed a pincer movement, one observing the searingly hot origin of the winds, the other chronicling their epic journey outwards. The era of speculation was over. The time for confrontation had begun. We were no longer just listening to the rhythmic pulse of the lighthouse. We were finally about to see the storm raging at its base. The first dispatches from this new frontier were bewildering. They pointed not to a gentle breeze, but to a focused, sustained blast of incredible ferocity. One of the earliest and most perplexing targets was a pulsar designated IGR J114 613. This wasn't just any stellar remnant. It was a runaway, a cosmic fugitive ejected from its birthplace by the supernova that created it, now hurtling through the Milky Way at over 5 million miles per hour. But its own motion was not the most shocking thing about it. Trailing behind this speeding corpse of a star, Chandra and Hubble revealed something utterly astonishing, a colossal jet of high-energy particles stretching for nearly 40 light-years. Think about that scale for a moment. A single structure perfectly collimated and arrow-straight 37 times longer than our entire solar system, from the Sun to the Oort cloud's edge. This was no mere exhaust plume. This was the work of a celestial blowtorch of incomprehensible power and endurance, one that had been firing continuously for centuries, perhaps millennia, as the pulsar blazed its path through the galactic plane. It was a fossil record of an ancient wind etched into the fabric of space itself. When the teams calculated the velocity needed to create such a structure, the numbers that came back seemed like a mistake. The particles in that jet, the very substance of the pulsar's wind, had to be moving at a staggering percentage of the speed of light. Not 1%, not 5%. The initial estimates, conservative and double-checked, pointed to speeds exceeding 80% of light speed. A river of plasma electrons and positrons being fired from a sphere just 12 miles wide with an energy that dwarfed our most powerful particle accelerators. You're now imagining a cannonball the size of a city firing subatomic bullets so fast they are nearly timeless. This was the observation. A stark, undeniable fact written in X-rays across a swathe of the sky. Now it was up to the theorists to explain it. And this is where the first cracks in our understanding began to appear subtle at first, but destined to widen into a chasm. The prevailing models for how a pulsar generates a wind were elegant, built on decades of work. They centered on the star's immense magnetic field 1,000 trillion times stronger than Earth's. As the neutron star spins with the frantic energy of a kitchen blender, this magnetic field whips around with it acting like a colossal electromagnetic turbine. This spinning magnetosphere was thought to create powerful electric fields strong enough to rip particles directly from the star's crust. Once freed, these charged particles, electrons and their antimatter counterparts, positrons, would be caught in the whirlwind. They would be flung outwards, riding the spiraling magnetic field lines like surfers on a cosmic wave, accelerated to incredible velocities. It was a beautiful idea, a perfect marriage of gravity, electromagnetism, and rotational mechanics. It had to be the answer. The models were run, the simulations programmed with the observed spin rate and magnetic field strength of IGR J1246103. The computers churned, calculating the maximum possible velocity this magnetic slingshot could impart. The result was a resounding failure. The models predicted powerful winds, certainly. They predicted relativistic speeds, yes. But they topped out at perhaps 30, maybe 40% of the speed of light under the most generous assumptions. They could not under any recognised physical process account for the sheer brutal velocity etched into that 40 light-year-long jet. There was a massive energy deficit, a gaping hole between the predictions of our physics and the reality we were now observing. It was like watching a child's pinwheel somehow generate a hurricane. The engine was too small for the output. The scientists were stumped. They tweaked the models, adjusted the parameters, questioned the fundamental assumptions. Could the magnetic field be shaped differently than we thought? Could there be some unknown amplification mechanism close to the star's surface? Every proposed solution felt like an ad hoc patch, an unsatisfying tweak to a theory that was supposed to be robust. The data from the runaway pulsar was an uncomfortable, inconvenient truth. It suggested the engine driving these winds was far more efficient, far more potent than our physics allowed. But an isolated pulsar, no matter how strange, could be dismissed as an anomaly, a cosmic freak. To truly prove the theory was broken, the observations needed to be repeated, confirmed in a different and even more extreme environment. And so the world's great observatories turned their attention to the neutron star binaries. These are systems of breathtaking violence, places where a neutron star is not alone but is locked in a gravitational death dance with a companion star. Here the neutron star's gravity is so powerful it actively siphons matter from its partner. A river of hydrogen and helium gas flows from the companion, forming a swirling incandescent vortex around the neutron star called an accretion disk. You must picture this disk not as a placid ring like Saturn's, but as a maelstrom of unimaginable heat and fury. As the gas spirals inwards, friction and tidal forces heat it to tens of millions of degrees, causing it to glow with the intensity of 1 billion suns in the X-ray spectrum. This is where our theories felt most confident. The accretion disk, we believed, was the ultimate engine. It provided a colossal reservoir of energy and matter, a perfect launch pad for an outflow. The physics seemed straightforward. The intense radiation pouring off the inner edge of the disk could act like a sandblaster, pushing gas outwards through sheer light pressure. Alternatively, the disk would generate its own fantastically complex magnetic fields, which, tangled and twisted by the disk's rotation, could grab hold of plasma and fling it away from the system at high speed. These were the textbook mechanisms, radiation driving and magnetic launching. They were the cornerstones of our understanding of cosmic outflows from newborn stars to supermassive black holes. For neutron star binaries, they were supposed to be the definitive answer. One system in particular became the crucible for these ideas, a chaotic binary known as Circinus X1. It is a strange and violent place, a young neutron star only a few thousand years old in a highly eccentric comet-shaped orbit around a massive supergiant companion. Once every 16.5 days, the neutron star plunges deep into the dense gaseous envelope of its partner, gorging itself on stellar material. During these feeding frenzies, the accretion disk flares to life with astonishing brilliance, and the system launches vast bipolar outflows, jets of matter screaming away from the poles of the disk. This was the perfect laboratory. We could watch the engine turn on and off with clockwork regularity. Using the incredible spectroscopic capabilities of Chandra and the European Space Agency's XMM Newton Observatory, astronomers could do more than just see these outflows, they could dissect them. By analysing the X-ray light passing through the wind, they could measure its properties with surgical precision, its temperature, its density, and most critically, its speed. They watched patiently as Circinus X1 made its dramatic orbital plunge. They saw the accretion disk ignite, and then they saw the wind. The spectrum of light shifted the telltale signature of the Doppler effect, revealing matter, moving at an incredible pace. But when the final velocity was calculated, a stunned silence fell over the research teams. This was no mere wind. This was an exodus of matter on an epic scale. The material erupting from Circinus X1 was moving at 10% of the speed of light. Let that number sink in. 30,000 kilometers per second. 67 million miles per hour. A sustained wide-angle outflow of superheated plasma moving fast enough to travel from the Earth to the Moon in under 4 seconds. This was not the finely focused pencil-thin beam of a pulsar jet. This was a broad, powerful blast carrying away a significant fraction of all the matter the neutron star was consuming. The sheer kinetic energy being unleashed was almost beyond comprehension. The observations were cross-checked with radio telescopes on the ground, which tracked the glowing knots of plasma as they propagated outwards for light years. The results were ironclad. The speed was real. The power was undeniable. Now the theorists had to face the music. They took their most sophisticated models, the pinnacle of computational astrophysics, and simulated the accretion disk of Circinus X1. They programmed in the immense gravity of the neutron star, the intense radiation field, the twisting magnetic fields generated by the churning plasma. They ran the numbers again and again, and again and again the simulations failed spectacularly. The radiation pressure from the disk. It could only push the wind to about 1% of light speed, a full order of magnitude too slow. It simply lacked the punch. The magnetic launching mechanisms, they fared a little better, producing faster, more collimated outflows, but they couldn't reproduce the sheer breadth and mass of the observed wind, nor could they consistently reach the blistering 10% velocity. The models had a fundamental energy problem. To launch that much matter at that much speed requires a certain amount of power, an energy budget that has to be paid. According to our physics, the only available power source was the accretion disk itself, fueled by the infill of matter under gravity. But the energy detected in the wind was a huge fraction of the total energy available in the entire system. It was as if a car engine wasn't just turning the wheels, but was somehow also ejecting its own component parts with the force of a bomb, all while continuing to run. The efficiency was impossibly high. The engine was by all accounts breaking the laws of conservation of energy, or at least our understanding of how that energy could be converted into motion. This wasn't just a small discrepancy anymore. This was a direct head-on collision between observation and theory. With IGR JM146103, we saw a focused jet whose speed we couldn't explain. With Socinus X1, we saw a massive wide-angle wind whose combination of speed and mass defied the very engine we thought was powering it. It was a crisis that rippled through the astrophysical community. At conferences and in university hallways, the conversations grew more urgent. The data was irrefutable, gathered by our most advanced instruments. The models built on the foundations of general relativity and magnetohydrodynamics were equally solid. Yet they existed in two different universes. One could not explain the other. This is a profoundly uncomfortable place for science to be. It is the moment when the elegant map you have been drawing for a century suddenly fails to represent the territory you are actually exploring. Every new observation of these extreme binaries seemed to only deepen the paradox. Systems like Scorpius X1 and Cygnus X2, long studied and well behaved in other respects, began to reveal winds with similarly perplexing characteristics when scrutinized with our new X-ray vision. The problem wasn't isolated, it was becoming endemic. The universe was showing us a mechanism for accelerating matter that was brutally effective, dwarfing anything our theories could conceive. We were like engineers in the 18th century staring at a bolt of lightning. Understanding that it was a form of energy, but having absolutely no grasp of the electromagnetic principles required to describe or harness it. We were witnessing a fundamental force of nature at play, a cosmic accelerator of profound efficiency, and we had no blueprint for how it was built. The neat and tidy physics of accretion of magnetic fields of gravity itself seemed to buckle under the strain of these observations. The universe wasn't just pushing the boundaries of our models. It felt as though it was actively mocking them, demonstrating a casual mastery of forces that remained utterly beyond our comprehension. The confrontation had yielded a clear victor, and it was not our understanding. We were left in the dark, holding a set of broken equations, staring at ghosts moving at impossible speeds. The very real and terrifying possibility began to dawn. Maybe our physics wasn't just strained. Maybe in the heart of these stellar monstrosities it was fundamentally incomplete. And so the equations fell silent. The elegant architecture of astrophysics, built over a century of patient observation and brilliant insight, offered no shelter from this storm. Every conventional model we aimed at the problem thermal expansion radiation pressure, the gentle nudges of photons simply disintegrated. They were theories built for a universe of familiar forces of comprehensible energies, but the winds screaming from these neutron stars were not familiar. They were an indictment, a howling refutation of our understanding, moving at speeds that belonged not to the realm of stellar mechanics, but to the fevered dreams of science fiction. The blackboard was wiped clean, not by a new discovery, but by a humbling, undeniable failure. In laboratories and university halls across the globe, a creeping sense of dread took hold. We were not just missing a variable or a coefficient. We had missed the entire story. This is the moment in science that is both terrifying and thrilling. It is the precipice of revolution. When the old maps lead you off a cliff, you have no choice but to redraw the world. The search for a new map began not by looking for a slightly faster wind, but by hunting for a fundamentally more violent engine. The astronomical community turned its gaze toward the true monsters of the stellar graveyard, the celestial tyrants whose very existence seems to mock the laws of nature. We had to look at the magnetas. If a typical neutron star is a cosmic cannonball, a magnetar is a thermonuclear god of destruction. These are the rare twisted siblings in the neutron star family, born from supernova explosions with a catastrophic, almost unbelievable magnetic peculiarity. Where a normal neutron star's magnetic field is already trillions of times stronger than Earth's, a magnetar's field is 1,000 times stronger still. It is a quadrillion times the magnetic field that guides your compass needle. This is not a difference of degree, it is a difference in kind. It is the difference between a candle flame and the core of the sun. A magnetar's magnetic field is so powerful it becomes a physical force capable of warping the very atoms of any material that dares to approach. It is strong enough to rip you apart from 100,000 miles away, not through gravity but by violently distorting the electron clouds that hold your molecules together. For years, magnetars were treated as exotic curiosities, too rare and too strange to be central to mainstream astrophysics. But in the face of the ultrafast wind enigma, that thinking began to change. Perhaps theorists whispered these weren't outliers, perhaps they were the key. Perhaps by studying the most extreme case, we could unlock the secret of the entire class. The magneta became our Rosetta Stone, a horrifying, beautiful inscription written in a language of impossible physics. Scientists began to realize that in such an environment, the magnetic field is no longer a passive bystander, a simple container for hot gas. It becomes the primary actor in the drama. It becomes the engine itself. This was the birth of a new paradigm. We had to abandon the simple physics of pressure and force and enter the dizzying world of relativistic magnetohydrodynamics. It's a mouthful, but the concept behind it is breathtakingly audacious. It treats the magnetic field not as invisible lines of force, but as a tangible physical fluid. Imagine a river of pure magnetic energy flowing, twisting and crashing through the space-time around the neutron star. This magnetic fluid is interwoven with a superheated plasma of charged particles, both bound together in a chaotic, inseparable dance. In this new model, the wind isn't a matter being pushed by the field. The wind is the field carrying matter along for the ride. The true genius of this idea reveals itself when you add the neutron star's ferocious spin. Remember, these objects can rotate hundreds of times per second. This isn't a gentle rotation, it is a gravitational vortex spinning at a substantial fraction of the speed of light. Now picture what this does to the magnetic river flowing from its surface. The magnetic field lines anchored to the star's crust are whipped around with unimaginable violence. They can't just spin along neatly, they're dragged, stretched and twisted into gargantuan complex knots. It is like taking thousands of elastic bands, pinning them to a spinning top, and watching them wind tighter and tighter and tighter. An unbelievable amount of energy, the rotational energy of a city-sized object, weighing more than the sun, is being pumped directly into the magnetic field, storing it as pure magnetic tension. This is the heart of the new theory, a cosmic magnetic slingshot. The winds are not a steady outflow, they are the catastrophic snap of these over-twisted magnetic field lines. When the tension becomes too great to bear the field lines violently reconfigure themselves, erupting outwards in a colossal release of stored energy. This explosion, this magnetic quake, flings the embedded plasma into space, is not a gentle push, it is a point-blank detonation. The particles are not just accelerated, they are launched riding a tidal wave of magnetic energy that propagates outwards at nearly the speed of light. This isn't a wind in any terrestrial sense. It is a relativistic magnetic bomb exploding continuously. The model predicted speeds that were for the first time in the same ballpark as the baffling observations. It was a brutal, violent and messy solution, but it had the ring of truth. It felt like physics that belonged in the hellscape around a neutron star. But even this radical idea was incomplete. It was a powerful engine, yes, but something was still missing. The sheer density of matter required to form these winds, the sheer number of particles needed to be launched, remained a profound puzzle. Where was all this material coming from? Even the thin atmosphere of a neutron star seemed insufficient to fuel such a relentless high-speed torrent. The answer would come not from the physics of magnetism, but from the deepest, most unsettling principles of Einstein's universe and the ghostly realm of quantum mechanics. It required us to accept that the space around a neutron star isn't empty at all. To understand what happens next, you have to confront one of the most profound concepts in all of physics frame dragging. According to Einstein's theory of general relativity, mass does not simply sit in space-time. It tells space-time how to curve, creating gravity. But a spinning mass does something more. It doesn't just curve space-time, it grabs, it twists it and drags it around in its wake. The neutron star is not merely rotating in a static universe. It is a cosmic blender churning the very fabric of reality into a swirling vortex. This is not a metaphor. Space-time itself, the three dimensions of space, and the one of time, is being literally and physically twisted by the star's rotation. Anything near it, light particles, even the magnetic field, is caught in this gravitational whirlpool. This space-time vortex dramatically amplifies the twisting of the magnetic field. The field isn't just being wound up by the star's physical surface, it's being sheared and tangled by the contorting geometry of space itself. This creates electric fields of an intensity that we can barely write down. The voltage difference over a tiny patch of the neutron star's magnetosphere can exceed trillions of volts. This isn't like the electricity in your home or even a bolt of lightning. This is an electric potential so extreme that it brings the universe to a quantum breaking point. It brings the vacuum to a boil. Here we arrive at the edge of known physics, a place where matter is forged from pure energy. According to quantum field theory, the vacuum of space is not a void. It is a roiling soup of virtual particles, pairs of electrons and their antimatter counterparts positrons, that flash into and out of existence for infinitesimally short moments before annihilating each other. They are ghosts in the machine of reality. Under normal conditions, they are fleeting and undetectable, a quiet hum beneath the surface of the cosmos. But in the titanic electric fields of the magnetar's magnetosphere, this quantum hum becomes a deafening roar. The electric field is so strong that it can grab these virtual pairs before they can disappear. It rips them apart, pulling the electron in one direction and the positron in the other, and slams them with so much energy that they become real, stable particles. Suddenly, out of the supposedly empty space, a cascade of matter and antimatter is born. A single high-energy photon generated in the magnetosphere can decay into an electron-positron pair. These new particles are then accelerated by the electric field radiating more photons, which in turn create more pairs. The result is an avalanche, a quantum firestorm, a self-sustaining cascade that floods the magnetosphere with a dense, superheated fog of freshly created electrons and positrons. This is the missing fuel. The neutron star doesn't need to scrounge for material from its own surface. It creates its own wind out of the quantum vacuum. It manufactures the bullets for its own machine gun, forging them from the energy of its own spin and magnetic field. This was the final staggering piece of the puzzle. The vision that emerged was as terrifying as it was beautiful. It begins with the colossal spin of a super-dense star, a gravitational gyroscope churning the fabric of spacetime. This spacetime vortex twists the star's godlike magnetic field into knots of unimaginable tension. As the field strains against itself, it generates electric potentials so vast they can tear the vacuum asunder, creating a self-sustaining storm of matter and antimatter. And then the final act, the magnetic field lines snap. They reconfigure in a violent explosion, a relativistic detonation that takes this freshly minted plasma, this ghost wind forged from nothing, and flings it into the cosmos at a third of the speed of the light. This was no longer just a stellar wind. It was a multi-stage relativistic engine of unparalleled efficiency. It was a machine that drew power from gravity, stored it in magnetism, and used it to convert the quantum vacuum into a directed beam of energy and matter. The scientific community stood in awe. The frustration of the failed models gave way to a profound sense of revelation. We had been trying to understand a thermonuclear explosion by studying the physics of a campfire. The problem wasn't that our physics was wrong. It was that we had never dared to imagine a place where so many disparate and extreme branches of physics, general relativity, quantum electrodynamics, plasma, physics could all come together in a single unified violent symphony. The neutron star wind was not an anomaly. It was a message that the universe still contained arenas where the fundamental forces could behave in ways we were only just beginning to comprehend. The clean blackboard was no longer a symbol of failure. It was an invitation to write a new chapter in the story of the cosmos, to explore a realm where space itself is a weapon, and the void is a source of fuel. We now had a theory, a radical, almost unbelievable narrative that seemed to fit the impossible facts. But a theory, no matter how elegant, is only a ghost story until it is confronted with proof. The next great challenge was clear to find the fingerprints of this incredible machine. In the light from these distant violent stars, the equations finally had yielded a phantom. Our supercomputers, labouring for months, had spun a tapestry of mathematics so complex, so counterintuitive, it felt less like a discovery and more like a fever dream. A dream, however, that produced the impossible, a theoretical mechanism capable of launching particles at 1,000 times the speed of our own sun's solar wind. We had a ghost in the machine, a plausible sequence of events where the unimaginable gravity and dizzying spin of a neutron star could conspire through a cascade of relativistic effects to create the gale forces we had observed. For a fleeting moment there in the silent glow of the monitors, it felt like victory, a solution, an answer. but science is rarely so kind. An answer, particularly one that strains the very limits of our understanding, is never just a destination. It is a doorway. And as we stepped through this one, we found ourselves not in a brightly lit room of certainty, but in a vast, darker chamber, echoing with questions far more profound than the one we thought we had solved. The model, our beautiful, intricate ghost, was not an answer at all. It was a map to a whole new continent of mysteries, and its existence forced us to confront consequences on a scale we were scarcely prepared to imagine challenging the very architecture of the cosmos. If this wind is real, if our phantom has a physical form, then it cannot exist in a vacuum. It is a cosmic actor, and it must play its part on the galactic stage. Out there in the seemingly empty void between the stars lies the interstellar medium. It is not a true emptiness, but a fantastically dilute soup of gas and dust, the raw material from which future stars and planets will be born. To us, it is a near-perfect vacuum more tenuous than anything we can create on Earth. To a particle screaming away from a neutron star at a significant fraction of the speed of light, this medium is not empty space. It is a solid wall. Imagine driving a vehicle at unimaginable velocity, not through air, but through a thick, viscous fluid. The resistance, the impact would be catastrophic. This is the fate of the neutron star wind. As this hyper-relativistic outflow, this celestial blowtorch slams into the ghostly tendrils of hydrogen and helium that litter the galaxy. It creates a spectacle of violence that dwarfs anything we have previously modelled. A shockwave forms, but it is no ordinary shockwave. It is a titanic structure known as a termination shock, a place where the rules of classical physics are shredded and discarded. Here the kinetic energy of a trillion tons of matter, moving at near light speed, is instantly converted into other forms. The collision zone becomes a particle accelerator of staggering efficiency, a cosmic crucible far more powerful than any machine we could ever build on our world. Particles in the interstellar medium once placidly drifting are caught in this maelstrom. They are battered, accelerated, and energized to levels that are simply breathtaking. The shock front would glow not just in visible light, but with the fierce penetrating glare of X-rays and gamma rays. It would become one of the brightest objects in the high-energy sky, a cosmic battlefront where the dead star's fury meets the galaxy's calm. Around the neutron star, a vast bubble would be carved out, a cavity of superheated turbulent plasmatons, even hundreds of light years across. This structure, this pulsar wind nebula, would be unlike any we have seen before. The ones we know, like the majestic Crab Nebula, are already monuments to extreme physics. They are powered by winds moving at perhaps 30 or 40% the speed of light, but a wind moving at over 99%, the resulting nebula would be an entirely new class of object. Its magnetic fields would be wound into impossibly tight complex geometries, acting as a magnetic bottle for particles of astonishing energy. It would pulsate not with the steady rhythm of the neutron star's spin, but with violent, unpredictable flares as the shock front encounters denser clumps of interstellar gas like an oceanic wave crashing against a hidden reef. We are forced to ask, are we seeing these structures? Have our telescopes already captured images of these hyper-energetic nebulae objects we have misidentified or simply classified as unusual because we lacked a theory violent enough to explain their existence? Perhaps some of those enigmatic gamma-ray sources, those points of light in the sky that defy easy explanation, are not distant black holes or colliding galaxies. Perhaps they are the signposts, the luminous wounds in the fabric of space that mark the impact zones of these very winds. We have been searching for the cannon, the neutron star itself. It may be that we should have been looking for the bullet hole. The implications of this cosmic collision ripple outwards far beyond the immediate vicinity of the star. A shock wave of this magnitude does not just heat the interstellar medium, it fundamentally changes it. It compresses the gas, pushing and squeezing vast clouds of hydrogen. And when you squeeze a cloud of hydrogen hard enough, when you increase its density beyond a critical point, something magical happens. It begins to collapse under its own gravity. The cloud fragments, condenses and heats up until deep within its core a nuclear furnace ignites. A star is born. Could it be that these dead stars, these tiny spinning embers left over from a supernova, are not just cosmic relics, but also cosmic catalysts? Could their ferocious winds be a mechanism for triggering the next generation of star formation, a violent but ultimately creative force that helps shape the evolution of an entire galaxy? It's a breathtaking thought. The universe, in its elegant and often brutal efficiency, using the death of one star to midwife the birth of thousands more. The neutron star, in its final energetic act, would be seeding its own legacy, sculpting the very galactic arm in which it resides. Over billions of years, the cumulative effect of thousands of such systems could be profound. They would be galactic gardeners tilling the soil of the interstellar medium, enriching it with heavy elements forged in their own supernova deaths, and then ploughing it with their winds to encourage new growth. And there is another even more tantalizing possibility. For over a century, we've been aware of a constant rain of particles falling on Earth from deep space. These are cosmic rays, atomic nuclei, protons, helium, and heavier elements stripped of their electrons and accelerated to colossal energies. The most powerful of these, the ultra-high energy cosmic rays, are a profound enigma. Each one carries the kinetic energy of a professionally thrown baseball packed into a single subatomic particle. They are the fastest things in the universe, so energetic that their origins defy our neatest theories. Supernovae can account for the lower energy ones. Active galactic nuclei, the supermassive black holes at the hearts of galaxies, can explain some of the more powerful ones, but there is a gap, a range of extreme energies for which we have no good explanation. We lack a known accelerator in our galaxy powerful enough to get a proton moving that fast. What if we've been staring at the answer all along? The termination shock of a hyper-relativistic neutron star wind is a particle accelerator of almost unbelievable power. The churning magnetized plasma at the shock front is the perfect environment for a process called Fermi acceleration, where particles are bounced back and forth across the shock-gaining energy with every single bounce. It is like a cosmic tennis match played with protons, where the rackets are magnetic walls moving at near the speed of light. Could these tiny city-sized objects be the source of our galaxy's most energetic particles? If so, it would solve one of the greatest outstanding mysteries in astrophysics. The messengers from deep space, the particles that tell us about the most violent processes in the universe, might be coming not from exotic distant galaxies, but from our own cosmic backyard, launched by the very stellar engines we are now struggling to understand. You're at this very moment being pierced by thousands of these cosmic rays. They are harmlessly passing through your body, but their existence is a testament to the violence of the cosmos. To think that some of them began their journey in the maelstrom surrounding a neutron star is to connect us physically to these incredible phenomena. And here, as we begin to grasp the awesome galaxy-shaping power of these winds, we slam headfirst into the most daunting mystery of all. A question so fundamental it threatens to bring the entire theoretical edifice crashing down. It is a simple question of accounting, of balancing the books. Where does all this energy come from? The sheer power we're talking about is difficult to express. The kinetic energy carried in this wind every single second could exceed the total energy output of 1 million suns. It is an energy budget that borders on the nonsensical. A neutron star is not a fusion-powered engine like a normal star. It is a corpse. It has no internal fuel source, so it must be paying this colossal energy bill from a finite bank account. That account has only two forms of currency: its rotational energy and its magnetic field. A neutron star is a gravitational gyroscope, a celestial flywheel storing an immense amount of energy in its spin. As it powers the wind, it must slow down. This is an inviolable law of physics, the conservation of energy. You cannot get something for nothing. Yet when we look at the neutron stars we suspect of powering these winds, their spin-down rate, the rate at which they are slowing, is nowhere near high enough to account for the energy we see. It's not off by a little, it's off by orders of magnitude. The books don't balance. It is as if you saw someone spending $1 billion a day, but when you check their bank account, you found they were only withdrawing 1,000. It makes no sense. The star is writing checks that its rotational energy budget simply cannot cash. How is this possible? Is there another energy source we have completely overlooked? Some exotic reservoir of power locked within the ultra-dense matter of the star itself? Perhaps in the quantum chaos of its superfluid core there is a mechanism for tapping energy that our physics doesn't yet recognize. Or maybe the efficiency of the conversion is the real miracle here. Somehow the star is converting its rotational energy into wind energy, with an efficiency that approaches 100%. In engineering and indeed in nature, such efficiency is a fantasy. There is always waste, friction, heat loss. Inefficiency is the universal tax on every energy transaction. Yet these neutron stars appear to have discovered a loophole, a way to cheat the cosmic taxman. How they achieve this is a complete blank. It is magic masquerading as physics. The mechanism eludes us, buried deep in a regime where gravity is so strong and quantum mechanics so strange that our two great pillars of 20th century physics, general relativity and the Standard Model, cease to provide clear answers. This is the point where the narrative of physics broken becomes truly unavoidable. Our beautiful model, the one born from our supercomputers, can create the wind, but it cannot explain how the star pays for it without destroying itself. It describes the what, but remains utterly silent on the how. The discrepancy is so vast, so fundamental, that it feels less like a puzzle to be solved and more like a signpost pointing toward a revolution. It suggests that our understanding of the universe is not just incomplete in its details, but that there may be a profound error in its foundations. We are being confronted with evidence that something new is at play. The universe is whispering to us from the hearts of these dead stars that there are rules to the game we have not yet learned. Perhaps the answer lies in the unification of gravity and quantum mechanics, the holy grail of modern physics. In the quantum foam that may exist at the neutron star surface, strange things could be happening. Virtual particles might be harnessed. Space-time itself might be twisted in such a way that it funnels energy with an impossible focus. It could be that the immense gravitational forces are modifying the behavior of fundamental particles, unlocking interactions and decay modes that are forbidden under normal conditions. Are we seeing the first macroscopic evidence of a theory of quantum gravity, or is it something else? A new particle, a new force, a new dimension of reality that only manifests in these most extreme of all cosmic environments. The neutron star is no longer just a fascinating object. It has become a laboratory for testing the absolute limits of knowledge. It is a place where our theories are stretched until they snap, and in the snapping we get a terrifying and exhilarating glimpse of the deeper, stranger reality that lies beyond. The phantom our computers generated has led us here to the edge of a cliff. Below us lies an ocean of ignorance, but on the far shore we can just make out the coastline of a new physics. The existence of these winds and the impossible energy they demand is a direct challenge. It tells us that we do not fully understand gravity. We do not fully understand matter. We do not fully understand energy. After centuries of thinking we were closing in on a complete picture of the cosmos, these tiny spinning cinders have thrown it all into question. They are not just a curiosity, they are a crisis. And in science, a crisis is another word for an opportunity. The opportunity to be wrong, to be humbled, and to begin the search anew, armed with the certainty that something incredible is waiting to be found. And so we found ourselves standing at the edge of an intellectual abyss, staring at a cosmic impossibility. The raw data screamed a truth that our classical models simply could not contain a velocity so extreme, it seemed to mock the very laws we held sacred. 1,000 times the speed of the sun's own wind, a torrent of matter hurled into the void by an engine whose power source remained shrouded in mystery. Faced with this defiant paradox, science did not retreat. It did not declare its laws broken. Instead, it did what it has always done when confronted by the unthinkable. It built a new window, a new lens, through which to see the universe not as we imagine it, but as it truly is. We had to abandon the familiar shores of our physics and journey into a realm where gravity bends light, where space itself is a dynamic fluid, and where magnetism holds the power of creation. We had to enter the ghost of a neutron star. This spectral realm exists not in the heavens, but inside the most powerful supercomputers ever conceived by humankind. Here, within digital crucibles humming with furious calculation, we can pour in the fundamental equations of the cosmos, the twin pillars of modern physics, Einstein's general relativity, and Maxwell's electromagnetism. We weave them together into a new, formidable tapestry known as general relativistic magnetohydrodynamics, or GRMHD. These are not mere animations, they are universes in miniature complex evolving ecosystems of physics, where we can unleash the full untamed ferocity of a neutron star and watch for the very first time the intricate dance of forces that unfolds in its immediate vicinity. Inside these simulations, we can finally witness the birth of the impossible wind. What they reveal is not a single simple mechanism, but a breathtaking cascade of violence, a chain reaction of physical processes, each more extreme than the last. The overture to this cosmic symphony of destruction begins with the star's magnetic field. You must picture it not as the gentle looping lines of a bar magnet, but as a monstrous tangled web of pure force, a cage of energy containing pressures 1,000,000,000,000 times greater than anything achievable on Earth. This field is anchored deep within the star's superfluid core, but it is constantly twisted and sheared by the star's ferocious rotation, a spin so rapid that the equator moves at a significant fraction of the speed of light. Gravity, the crushing weight of a sun compressed into a city, holds the star together, but the magnetic field strains against it, storing energy in its contorted lines, like 1,000,000,000,000 coiled springs being wound tighter and tighter. For a time, an uneasy equilibrium holds. The field writhes a nest of captive serpents, but it does not break. Then inevitably 2 opposing field lines, stretched to their absolute limit by the star's relentless spin, are forced into catastrophic proximity. In the space between them, the pressure becomes infinite, the tension unbearable, and in a flash of unimaginable brilliance they snap. This is magnetic reconnection, but on a scale that defies all terrestrial comparison. It is not a spark, it is a cosmic short circuit that unleashes the energy of 1,000,000,000 solar flares in a microsecond. The stored magnetic tension is converted with near-perfect efficiency into raw kinetic energy and radiation. A celestial lightning bolt forged from the fabric of space-time itself cracks across the magnetosphere and the storm begins. This titanic explosion of energy doesn't just radiate outwards, it slams into the surrounding plasma, the thin veil of charged particles trapped in the star's magnetic grip. The impact generates a shock wave, but this is no ordinary disturbance. It is an ultra-relativistic shock, a tsunami of pure energy moving at over 99.9% the speed of light. This wavefront is a place where the normal rules of matter cease to apply. It is a physical discontinuity, a wall of compressed plasma and electromagnetic fields so energetic that it glows with the light of gamma rays. As this celestial blowtorch scours the surface of the magnetosphere, it acts like a particle accelerator of breathtaking power, grabbing the ions and electrons caught in its path and instantly kicking them up to near-light speeds. Here we found the first part of our answer. Magnetic reconnection provides the raw explosive power, and the resulting shockwaves provide the initial violent shove. It was a staggering leap forward in our understanding a mechanism that could plausibly generate speeds far beyond what thermal pressure alone could explain. For a moment it felt like we had solved the puzzle. The simulations bloomed with these shock fronts, and we could trace particles being swept up in their wake, accelerated to phenomenal velocities. Yet even this was not enough. The calculations showed that while the shocks were immensely powerful, the sheer density of the plasma they were pushing acted as a brake. Trying to accelerate a traditional plasma of protons and electrons to 1,000 times solar wind speed is like trying to make a hurricane push a freight train to the speed of sound. The inertia of the material was simply too great. The engine was powerful, but the payload was too heavy. The paradox remained diminished but not defeated. The simulations were telling us we had the right engine but the wrong fuel. There had to be another component, another piece of the puzzle, hidden within the maelstrom that we had not yet accounted for. The answer when it came was not found in the matter that was already there, but in the creation of new matter from the vacuum itself. The energy densities within the reconnection zones and the shock fronts are so colossal, so far beyond anything we can comprehend, that they begin to warp the very fabric of reality. Here in these fleeting hotspots of unimaginable power, Einstein's most famous equation, MC2, ceases to be a theoretical concept and becomes a literal ongoing manufacturing process. Pure energy is converted directly into mass, but it is not ordinary mass. The universe in its elegant symmetry demands a balance. When energy becomes matter in these extreme environments, it does so by creating particle-antiparticle pairs. For every electron forged from the light, a positron, its antimatter twin, is born alongside it. A phantom fog of matter and antimatter, an electron-positron pair plasma materializes out of nothingness, conjured into existence by the sheer fury of the star's magnetic death throes. You are witnessing the ultimate alchemy not lead into gold, but light into substance. This sea of newly born ghost particles is the missing key, the crucial ingredient that finally resolves the impossible speed. Why? Because this pair plasma has a truly unique and wondrous property. An electron and a positron have the exact same tiny mass but opposite charges. When you create a plasma from them, you have a medium that is incredibly responsive to electromagnetic fields, yet it is almost unimaginably lightweight. Compared to a normal plasma of heavy protons and electrons, this pair plasma has virtually no inertia. It is a weightless ethereal wind, a perfect fluid for a cosmic accelerator. Now, when the magnetic reconnection events detonate, and the ultra-relativistic shocks propagate, they are no longer pushing a heavy cumbersome freight train. They are pushing a cloud of ghosts. The simulations now incorporating this final exotic piece of physics came alive. We could see the process unfold with stunning clarity. The coiled magnetic field lines snap, creating a reconnection point that blazes with the energy of 1 trillion suns. This energy instantly cooks the vacuum, birthing a dense cloud of electron-positron pairs. Almost simultaneously, the shockwave from the reconnection slams into this newly formed pair plasma. With nothing to hold it back, no inertial anchor weighing it down, the plasma is accelerated almost instantaneously. It is caught focused and fired outwards by the reconfiguring magnetic field lines, which now act like a cosmic railgun, a magnetic nozzle channeling this ghost particle sea into a tightly collimated, terrifyingly fast jet. This is the Neutron Star Wind. It is not a single steady breeze, but a relentless pulsating storm of magnetic explosions and shock waves, each one manufacturing its own lightweight ethereal fuel before firing it into space. It is a multi-stage accelerator built by nature, operating on principles so extreme they border on the magical. The mystery of the speed was solved not because our physics was broken, but because we had never witnessed physics operating under such tyrannical conditions. The forces at play are so titanic that they don't just move matter, they create it, and then accelerate that freshly minted matter to speeds that shatter our expectations. The neutron star, it turns out, is not just a gravitational anchor or a magnetic dynamo. It is a factory and assembly line for speed, converting the rotational energy of a collapsed star into the fastest sustained material flows in the known universe. Think of the sheer ingenuity required to uncover this. For decades, we were trapped staring at a number that made no sense. We built bigger telescopes, gathered more precise data, and still the paradox held. The solution did not come from a single heroic observation. It came from thousands of scientists and engineers painstakingly writing millions of lines of code, refining theories, and running simulations for years on end. They built a virtual cosmos in a box to solve a riddle posed by the real one. They had to teach a computer how to simulate the warping of spacetime, the behavior of plasma at near-light speeds, and the creation of matter from raw energy all at the same time. It is a testament to the relentless, stubborn curiosity of the human mind, a refusal to accept that the universe can be incomprehensible. The broken physics we started with was an illusion, a phantom born from our own limited perspective. The universe has no obligation to conform to our intuition, which is honed by the gentle, placid conditions of life on Earth. Out there in the crucible of a neutron star's magnetosphere, the full grandeur and violence of the laws of nature are on display. We had not been seeing a contradiction, we had been seeing a revelation. It was a message from the cosmos telling us that our understanding was incomplete, that there were new chapters of physics waiting to be read, written in the language of gamma rays and ghost particles. We were not witnesses to a failure of science, but to its greatest triumph, the ability to venture into the unknown, to grapple with the impossible, and to return with a deeper, more profound and far more beautiful understanding of the universe we call home. This resolution, however, is not an ending. It is a dramatic new beginning. Now that we understand the engine, now that we have unravelled the violent mechanism that creates these extraordinary outflows, we are forced to confront an even larger question. What happens when this wind, this relentless torrent of matter and antimatter, moving at a third of the speed of light, finally escapes the confines of its parent star? What happens when this celestial blowtorch, operating for millions of years, carves its way through the interstellar medium? We have solved the mystery of the wind's origin, but in doing so we have unleashed a new force upon our cosmic narrative. We must now turn our gaze outwards, away from the star itself, and follow this incredible wind on its journey into the galaxy, to witness the creative and destructive power it wields on a truly galactic scale. The story of the engine is over, the story of its impact is about to begin, and so the mechanism stands revealed. A dizzying dance of magnetic fury and warped space-time, a celestial engine tearing particles from the void and flinging them across the galaxy. We have followed the light from these cosmic spectres, deciphered the codes hidden in their X-ray signatures, and built simulations that echo their impossible power. We have in a very real sense stood at the edge of a phenomenon that should not exist and forced it to give up its secrets. But to believe our journey is over would be to misunderstand its very nature. The answer to one question is merely the key to a door behind which lie 1,000 more questions, each more profound than the last. We began this exploration with a simple, bewildering number, a wind moving at nearly 1/3 the speed of light, a velocity so immense it seemed like a malfunction in our instruments, a ghost in the data. It felt like a violation. All our understanding of stellar evolution, of the delicate balance between gravity and pressure that governs the lives of stars, seemed to crumble before this single fact. We knew that neutron stars were the crushed remnants of supernovae objects of incredible density, where a teaspoon of matter would outweigh a mountain. We understood them as pulsars, cosmic lighthouses spinning with a regularity so precise they were once considered evidence of extraterrestrial intelligence. They were the universe's most perfect clocks, their stability a comforting anchor in a chaotic cosmos. Yet this violent ultra-relativistic outflow was something else entirely. It was not the gentle pulsar wind we had modelled for decades. It was a tempest, a celestial blowtorch of such ferocity that it defied our most robust theories. It was as if a finely tuned Swiss watch had suddenly sprouted a volcano. This paradox was our starting point, the grain of sand in the oyster that would, through years of painstaking observation and theoretical struggle, create a pearl of new understanding. Our path from that initial bewilderment was not a straight line. It was a twisting, complex trek through the most extreme environments the universe has to offer. We had to abandon our comfortable notions of plasma physics, forged in the gentle confines of our own sun, and venture into a realm where the rulebook is rewritten. We first looked to the raw rotational energy of the neutron star itself. We imagined this spinning behemoth, a city-sized sphere with the mass of a star acting as a colossal flywheel. We saw how its magnetic field, 1 trillion times stronger than Earth's, could act as a magnetic sling grabbing charged particles and accelerating them to incredible speeds. For a time this seemed plausible. It was elegant, powerful, and it fit some of the data. But it couldn't account for the sheer focused violence we were witnessing, especially in binary systems where the wind carved immense shockwaves into the stellar material of a companion star. The numbers, when we ran them through our most sophisticated models, stubbornly refused to add up. The engine was powerful, but something was supercharging it beyond its known limits. This shortfall forced us to look deeper, to confront the more exotic members of the neutron star family. We journeyed to the magnetars, those terrifying celestial monsters whose magnetic fields are the strongest in the known universe. Here the very fabric of the star's crust quakes and shatters under the magnetic strain, unleashing cataclysmic flares of gamma-ray starquakes that release more energy in 1/10 of a second than our sun will in 10,000 years. We theorized that these sudden, violent magnetic reconnection events, like cosmic short circuits on a galactic scale, could provide the explosive injection of energy needed to drive the winds to their observed velocities. This was a crucial piece of the puzzle, a link between the star's internal magnetic turmoil and the external fury of its outflow. We were no longer looking at a steady, smooth process, but a chaotic, unpredictable storm fueled by the beast thrashing within its magnetic cage. Yet even this monumental force was not the final answer. The ultimate key, the secret ingredient that pushes these winds past the threshold of impossibility, was found not just in the star's magnetism, but in its other defining characteristic, its gravity. We had to embrace the universe as described by Einstein, a universe where mass does not simply pull on things, but fundamentally warps the geometry of space and time. A neutron star's gravity is so intense that it drags the fabric of space-time around with it, as it spins an effect known as frame dragging. It creates a gravitational vortex, a whirlpool in the cosmos itself. It is here in this swirling maelstrom of distorted reality that the final acceleration takes place. Particles caught in this gravitational gyroscope are not just flung outwards by magnetic fields. They are surfing on a wave of space-time itself, propelled by the raw, unadulterated power of a spinning gravitational singularity. The star's rotation, its magnetic field, and its crushing gravity are not three separate forces. They are a trinity, a perfectly unified system, a symphony of extremes that work in concert to create the universe's most efficient particle accelerator. In reaching this understanding, we have done more than simply solve a baffling astronomical mystery. We have realized that these objects are not mere cosmic curiosities, not just the burnt-out embers of long-dead stars. They are in fact the most profound laboratories for fundamental physics imaginable crucibles, where matter energy and space-time are pushed to limits we could never hope to replicate on Earth. Within the heart of a neutron star, protons and electrons are crushed together to form a sea of pure neutrons, a state of matter so bizarre it is governed by the strange laws of quantum mechanics. We call it neutronium, but this is just a label for something we barely comprehend. Its properties, its very existence, test the limits of our standard model of particle physics. Some theories suggest that deep within the core the pressure becomes so immense that even neutrons break down, dissolving into a quark gluon plasma, the primordial soup that existed in the first microseconds after the Big Bang. A neutron star, then, is a fossil of creation, preserving a sample of the universe's birth in its gravitational prison. Its winds are a direct probe into this extreme environment. By studying the composition and energy of the particles in these outflows, we are indirectly studying the physics of the star's core. We are analysing the exhaust from an engine built from alien matter, and from it we can infer the nature of the fuel. This is high-energy astrophysics in its purest form. These winds, as they slam into the interstellar medium or the atmosphere of a companion star, generate showers of gamma rays, X-rays and cosmic rays, the most energetic particles in the universe. They illuminate the complex web of interactions that govern our galaxy, seeding it with energy and shaping the formation of new stars and planets. They are not isolated events. They are an integral part of the cosmic ecosystem, a violent but necessary process of galactic recycling and renewal. Furthermore, these systems provide the most stringent tests for Einstein's theory of general relativity. In the placid environment of our own solar system, gravity is a gentle, predictable force. We see its effects as elegant elliptical orbits, but near a neutron star, gravity is a monster. Space-time is not just curved, it is bent to its breaking point. We can see the light from background stars being warped around the neutron star, a phenomenon known as gravitational lensing. In binary pulsar systems, we can watch the orbits of two such stars decay over time as they radiate energy away, in the form of gravitational waves, ripples in the fabric of space-time. This was the first indirect proof of their existence, a discovery that earned a Nobel Prize and opened a new window onto the universe. With every observation of these extreme systems, we push general relativity harder, searching for the point where it might finally break the point, where it must give way to a deeper, more complete theory of quantum gravity. So far, Einstein's theory has passed every test we have thrown at it, a testament to the power of a single human mind to grasp the fundamental workings of the cosmos. Neutron stars are the proving ground, where this legacy is continually reaffirmed. This journey from a single anomalous data point to a new understanding of fundamental physics is the very soul of the scientific endeavour. It is a story of human curiosity refusing to accept an easy answer, of pushing our technology and our intellect to their absolute limits. We built telescopes that can see the flicker of a candle on the moon. We designed detectors that can feel a ripple in space-time smaller than the width of a proton. We harnessed supercomputers that can simulate the cataclysmic merger of two neutron stars, a computational feat that models the interplay of general relativity magnetic fields and nuclear physics in a fraction of a second. Each step was born from the last, a chain of innovation driven by a relentless desire to know, and the quest is far from over. What we have learned has only shown us how much more there is to discover. We stand at the shore of a vast cosmic ocean, and the journey we have just completed has merely taken us from the shallows into the deep water. The next generation of instruments is already on the horizon, poised to peel back even more layers of this impossible onion. The Square Kilometre Array, a continent-spanning radio telescope, will map the magnetic fields around neutron stars with unprecedented precision, allowing us to see the structure of the engine that drives these winds. Future X-ray observatories, like the proposed Athena telescope, will have the sensitivity to measure the subtle distortions in space-time, right at the star's surface, providing a direct test of frame dragging and the nature of ultra-dense matter. Gravitational wave astronomy, still in its infancy, promises to let us not just see, but hear the universe. By listening to the cosmic chirp of two merging neutron stars, we can learn about the properties of neutronium in a way that is impossible with light alone. And our computational power continues to grow exponentially. Soon our simulations will not be mere approximations. They will be virtual universes, digital laboratories, where we can conduct experiments on neutron stars that would be impossible in the real world, testing our theories with a fidelity that was once the stuff of science fiction. Each of these new tools will undoubtedly bring new surprises, new paradoxes, that will challenge our assumptions and force us to rethink our models once again. Perhaps we'll find that the winds are even faster than we thought, powered by a mechanism we have not yet conceived. Perhaps we will discover that the matter inside a neutron star is even more exotic than we can currently imagine, a new state of reality governed by a new set of physical laws. This is the beauty and the terror of cosmology. The universe is under no obligation to make sense to us. Its truths are not constrained by our imagination or our mathematics. We do not get to dictate the rules, we can only hope to discover them. The neutron star, this crushed heart of a dead sun, is one of our greatest teachers. It is a relic from a more violent time in the universe, a silent monument to the awesome power of nature. And so we find ourselves at the end of this chapter, but not at the end of the story. We have stared into the heart of a cosmic furnace and emerged with a deeper, more profound respect for the universe we inhabit. We have learned that the empty space between the stars is not empty at all, but is crisscrossed by invisible hurricanes of unimaginable power. We have seen how the death of a star can seed the cosmos with the energy and the particles needed for new life. And we have been reminded in the most dramatic way possible that our understanding of reality is always incomplete, always a work in progress. The universe does not give up its secrets easily. It guards them in the crushing gravity of a neutron star, hides them in the fury of a magnetar's flare, and whispers them in the faint ripples of space-time. Our challenge is to keep listening, to keep looking up, not with fear, but with a relentless and unyielding curiosity. Because out there in the dark, a billion stellar engines are spinning and they have so much more to tell us. The wind is rising and our journey has just begun.